Here's my binding music. Okay. Probably pretty much got a quorum. A few people might drift in. So, in order to pretend that we've got an overall structure for this course, we have talked about transactions a bit, because transactions are really cool things. And then we talked about distributed systems a bit, and there's a lot more to talk about there. And we did it in that order because what we want to do now is to do some more work on transactions. And in particular, later on, we'll talk about distributed transactions. So we do a bit about transactions, a bit about distributed systems, and now we're going to talk about transactions over distributed systems later on today. But before we get to that, there's a whole lot more stuff on transactions anyway, because I quite like it. It's all implementation-y. I'm a systems implementary type person, so I like implementation details. But the real reason it's important is that it gives you an understanding how this stuff all works. And if you understand how it works, you have an understanding of its limitations and of its performance characteristics. So it may surprise you, but transactions are not built from fairy dust. It would be nice if we could use fairy dust, but we don't use fairy dust. Fairy dust has its own unique properties, but we don't use it. So what I'll do tonight is talk about the techniques we do use, because they're really widely applicable techniques and they're not fairy dust. But if you understand how they work, then you understand why I can't use this technology in this place, or if I use it, I've got these expectations and these performance penalties and these implications. So that's why we're doing more in-depth work on transactions, apart from the fact that I really like it. So eventually tonight we'll do distributed transactions, but we'll start off by doing more work on transactions and their implementation. So going back a couple of weeks ago, we talked about transactions. It's, in IBM jargon, used to be called a unit of work, which is not a bad word. So it's a collection of one or more operations working on one or more data resources, and it forms a single thing that will take the system from a state to another state, the entire system. So a transaction performs a state transition. And transferring money, purchasing a group of products in one go, booking seats, etc. And we talked about ACID, the made-up acronym, the atomic. We'll talk a lot about how we implement atomic. Consistent, nothing to do with the transactions. It's up to the application program to write their code so they go from a consistent state to another consistent state. You can have a transaction support system and write code that totally destroys your system consistency. That's your choice as the application programmer. But if you do write code that goes from consistent state to consistent state, then all the mechanisms of transactions will help you maintain that consistency in the face of things like failure. Isolation is the other main thing I'll be talking about tonight, that writing concurrent code is really hard. Have you written multi-threaded code and sort of low-level stuff? It's really hard. You have to worry about clashes. You have to worry about locks on the right things at the right times. You have to worry about lock starvation. There is 50 years of theoretical computing research in this area. It started in the 50s and 60s with work on concurrency control, and it was a very fruitful area of research for several decades. Have you heard of a guy called Esker Dijkstra? D-J-I-K-S-T-R-A. He was an early, very important computer scientist, and he made his reputation on working on concurrency mechanisms. And when I was preparing some of the stuff on this today, there's all this heroic work done but none of which actually applies today, because now the computer architectures are different, and we use hardware primitives that weren't available then. But if you do the stuff that was done in the 60s, they assumed very simple processes, in-order processes. These days we have out-of-order processes and parallelism, so all of that work doesn't actually work anymore. But it's okay, we have much better alternatives. So, isolation. Concurrency is hard when we're accessing shared resources. We get support with that. And durable. Really important, and we'll do all of that with absolutely minimal programmer effort. And we're interested in all this because we want to build high-performance, reliable, scalable systems. And it's really choose 2 out of the 3 there. You will pay for something with one of those. But the way we're going to get close to it is using lots of parallelism, lots of concurrency, and distributing our computation across multiple systems. And writing that type of code is hard. Writing reliable, parallel distributed code is not an easy task, where not easy means pretty close to impossible. Yes, you can do it if you're NASA, or if you've got that level of resources, but it's not an average programmer task. Transactions create an illusion of a simple sequential world where we can have multiple concurrent running programs, but they don't interfere with each other. And we do that lack of interference, the isolation, by transparently pausing pieces of code. So if there was going to be a collision, we simply pause one of them, let the thing that would have collided with it finish, and then we'll run the next one. We'll just let things run in parallel and magically, using the fairy dust, work out when there was likely to be a collision, and if there's a collision, just shift one of the operations in time so the collision is avoided. That's what we do. And we do it using fairy dust. So we run in parallel wherever possible, and then we serialize when there are potential conflicts. And going back to the consistency, we also want to maintain the consistency, the integrity of our system despite failures, and that includes all types of failures. Hardware failures, system software failures, application program failures. I know that the code that you people write never has bugs in it, never when it goes into production at least, but some people write code with bugs in it. So we want to be able to have a reliable system despite all those issues. So we want to be able to recover from transient errors. So deadlocks we talked about are a classic transient error. So if I did have 2 pieces of code and they didn't interfere with each other, then if I ran them again, their timing would be different and they probably wouldn't deadlock. So a perfectly good way of handling a lot of errors in these systems is I'll just try it again. And it works because I've changed the timing. I've changed the relative timing, and the problem was a timing problem. So do it again. Hey, it works this time. It's not good luck. It's just I'm solving a timing problem. And other application errors may or may not work again just because the data they're working on might be now in a more stable state, and who knows what caused the application, but retrying it is not a bad thing to do. We want to recover after system failure, all types of system failures, including network failures. We always have to fail cleanly, which means we fail back into a good, consistent state, with all the integrity rules of our business still intact after the recovery. No money missing, no seats that are in a state where it's neither booked or available. Whatever the integrity rules of our business, they still hold. And of course, we go back to what the application programs do with the C part of the acronym. They take you from a system where all these integrity rules apply to another state where they apply. And in between, they don't apply because it's taken money out of that account, hasn't put in there yet, but that intermediate state is not visible. So the external view is always a consistent state. Good. We get that high reliability through a lot of mechanisms, some of which we'll talk about later in the course, but it's all based on redundancy. We have multiple systems. We might have standby systems, warm standbys, hot standbys. We might take a workload and partition it over two systems and work out some way of keeping them in sync. And then if one of them falls over, the other one just has an increased workload but keeps on going. So we don't have a failure there. We just swap the workload and perhaps slow things down a bit. So clustering, load sharing. These days we might have virtual resources, in which case the resource is only virtual. Oh dear, that VM died. We'll just move it to another VM on another machine. Boom. So we just take that environment and the workload is processing and move it and magically pick up the state that was there as well. And we'll do that because the state's going to be kept on some other redundant resilient state store, which is outside the VM. So the computational task moves to another VM on another machine and then recovers its state from the external persistent reliable state store. And we keep on going. No one knows the machine died. And if we really get fancy, we can do geographic redundancy. If you're using the likes of Amazon or Azure, you can say, I want to geo-replicate this system and have a system in this country and one over there, and if this fails, something happens to the Sydney data centre, it's okay, we'll just pick it up somewhere else, geographically separate. So lots of work on redundancy, some of which we'll talk about when we talk about cloud stuff. And a lot of this is based on transactions and the technologies that were originally developed for and associated with transactions, particularly on logging and acknowledged rights. So we say, put this to the persistent store and tell me when it's there and don't lie to me, because most times storage systems will lie to you, so you've got to make sure they're not lying. There's a whole lot of distributed computing work on quorum sensing and saying, well, I told you all to write this down. Have enough of you written it down so that if something happened, we could get the answer back again. So there's a lot of distributed computing theoretical research on how to build robust systems from multiple components, having them vote on things and saying, yes, this is the right answer. If you're doing aircraft design, system design, you may think that's a great idea, particularly if you're doing flight control systems. But we won't talk about Boeing's current problem, who didn't do that. Okay. And a lot of the actual systems are based on transactional building blocks because that just removes one whole layer of complication. A little bit of history, partly because I think the first part was absolutely fascinating. The very first transactional systems were developed in the 1960s, and they were airline reservation systems. They were custom-made systems for airline res. They were the very first transactional systems. So a lot of the concepts came from that. And there was one called Sabre, and it supported 300,000 terminals. These would be teletypey things sitting in a travel agent's office. It could handle 4,200 requests a second. It had a custom operating system to run it. it probably had the computing power of my watch, or a bit less. So it would have been running on I suspect it wasn't Valve, it would have been pretty close to being a very early silicon machine, produced custom as well. This is pre IBM 360s. This would be, if it was an IBM machine, it might have been a 7090, but large, not very powerful by today's standards. But those numbers are highly respectable by today's standards. So a lot of very clever programmers writing very minimal, fast code. If you think about the number of operations we're doing per second, you're not clocking at nanoseconds there, you're probably clocking at tens of microseconds. So you don't get very many instructions per reservation order to actually, that's your budget is 50 instructions, that's it. You must do the transaction in 50 instructions, that's your budget. So remarkable achievement for the time. And they kept on running it for decades, of course, because it works. And then in the 70s, that type of, the techniques, the technologies became mainstream in banking, government, etc. So IBM, first of all, had IMS, which was a database system with transactional stuff built into it. And they had later on had a transaction monitor called KIX, which is probably still in use. Your bank probably runs KIX. If it has any IBM mainframe stuff around, it's probably running KIX. So if you can't take out and shoot because it's too embedded in the system. So KIX is still in use. I'm sure we could find KIX applications around. KIX COBOL was the canonical one. And all the other mainframe manufacturers all had their own equivalents. And they ran on large, expensive computers. The 80s mini computers came in, mostly Unix systems, and the same type of stuff there. We had what are called TP monitors then developed. Tuxedo and Chino, top end, were popular. A version of KIX was ported over to Unix as well. And then as OO programming came in, people wanted object transaction monitors, so we had object transaction monitors linked into Corva. And the database, commodity databases came into being as well, so Oracle, Sybase, Informix came into existence at that time, and they have transactional support buried inside them as well. And so we have this sort of coexistence now of the traditional mainframe stuff and this new world of Unixy, much lower priced. And then when we went from that world to microcomputers and Windows and Linux, etc., then this stuff just came with it. Then it became part of the plumbing. So on this HP box here, it's running Windows. There's a distributed transaction coordinator built into the plumbing. You might have to tick a box saying run it, but it's there as part of the Windows distribution. And if you're building commercial systems with .NET or J2EE, then transactions are just part of your environment. It's become commodity pervasive. And of course still being used everywhere else as well. That particular transactioning model was great, except we're now moving to web services, cloud-based systems, internet scale applications, and it doesn't work there, which is a shame. And the problems are scale, particularly trust, and I'll talk more about that later, the semi-connected nature of it all, and the latency. You send a request somewhere, it might take a second or 2 seconds to come back, and some of these technologies just don't work with that type of latency. They're built around the idea we're doing something really fast and really local, and now we're talking about an internet-sized thing. So there are lots of architectural and technology challenges when you're trying to build systems of that scale, which we'll talk about in a future lecture. So sort of futurish today, we do have web services transaction standards, which we'll talk more about in a later lecture. So there are a set of XML-based standards, which I showed you a pretty picture of a SOAP request the other day. It's a web services standard. So the people doing web services built a full, rich, full-fat, distributed computing platform based on XML and web standards, and included in that are 2 transaction standards. WSAT for tightly coupled ACID type transactions, and a loosely coupled thing called, I haven't used it, I've written papers on it. WS consistency? There is another transactional model which is a Sagas type model that I'll talk about later, which has never seemed to have taken off. And people are still using transactions of some kind. They're using between the components of a distributed application, they're using something between organisations, and they're using something between business processes. And the challenge is, what bits of transactions do I use, which ones are appropriate for particular architectural requirements, and can I live with partial consistency, or a term that's in use which is eventual consistency. Things may go out of consistency, but eventually they'll come back into being consistent. And a lot of that work was driven by people from Amazon who are trying to build systems of that scale where the traditional techniques just don't work. So we'll talk about those different consistency models when we talk about those types of systems in a few lectures' time. So, ACID, local transactions, the key assumptions are short duration, trusted participants, and what we're going to talk about now is how do we get most of those properties and what are the implications of them for the performance, scalability, etc. So, what can go wrong in a system? Well, applications can fail or otherwise decide that they've had enough and need to roll back. And at that point in time, they will have put the system in an inconsistent state. So we have to worry about getting out of that inconsistent state. The system can crash. When a system crashes through a transient software or hardware failure, then in today's technology, all the stuff that's in memory goes. We've lost memory. So all the state that's in memory, gone. And when we come back, then I've got bits of persistent state, and they may be not consistent. So a database is a typical example, which I'll talk about later. I've got persistent state written in at least two places in my database. I've got it in the files that represent the database tables, but they are deliberately out of date. They do not represent a consistent view of the world, because if they did, the performance would be so slow we couldn't use the system. And we have another version of the database which is consistent but unusable. So here we've got, in the real world, when we're actually running, we complement they all work together to produce a single consistent database view. But when we have a failure, 1/3 of that information was the stuff that was in memory is gone, and we have to reconstruct that from all the other pieces and bring the bits that are inconsistent, bring them up to the consistent state. But we'll talk about that later tonight. That's what the state conflicts on recovery mean, that the bits we do have after recovery may be inconsistent, so we have to solve that problem. And we can also lose persistent storage. Persistent doesn't mean guaranteed to be persistent, it just means it's not lying to us when it says it's got a copy of it. So we have to cope with the fact that our persistent storage can have disasters as well. We lose the storage, we get a failure. Oh dear, that was our persistent storage of something, now we've got to recreate that. So how do we do that? We're sort of at a minor, there are transition points in the industry. So for a long time, when these slides were given last year, a lot of the words for, I use the word storage here because I'm being correct. But last year they would have said disk, because that's what people kept storage on. And over the last few years, the big change has been going from spinning rust to solid state storage. And now we get different classes of solid state storage we're now getting to the type of solid state storage which can be really fast. So you're now getting pluggable on the memory bus persistent storage. So, and we haven't really quite worked out how to use that yet. But a lot of this type of technology is in this rapid transition as we go from algorithms that were developed to handle slow mechanical drives to, oh, we don't need to do that anymore. Perhaps we can radically change the architecture and not bother with a whole swag of techniques that were there to give good performance out of a slow medium. And now we're still midway through that transition. We'll be at the point not very long from now where we'll also have persistent memory as well as persistent storage. So when we lose memory, so when we lose power, we may lose some of our memory, but other memory will be persistent. So now all these things about how to recover will be totally different again, because now we've got another bit of persistent storage that will recover from power failure. But that won't be good enough because you could lose that as well, right? So there'll be multiple levels of recovery here. And the other major problem that can go wrong is people write code that walks over each other. So we have interference between concurrent applications, and questions there are, is only data from a consistent state visible? So I'm in the middle of updating something. Does any concurrent program see what I'm doing? Is it visible? Or can other programs get a snapshot of the world where they only see a consistent view of the world? Then they can go and muck around themselves and move to another consistent view, but they can never see inconsistent state. And a way of saying that is uncommitted data, data that is not, yes, I'm now in a consistent state. Is that visible? And we'll talk about some of the implications of that later on tonight. Okay, so applications fail. Well, they probably made some changes. It's great if they've done read, 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 oh dear, I'm dead. But it's more likely they've done read, read, update, update, dead. And so having made some changes out of a set of changes that need to be made to get to the next consistent state. So integrity constraints may well be violated by a failing program. And we want to make sure that failing programs, failing transactions, if they're transactional programs, have absolutely no effect. So we just want to roll them out. And the problem is, what happens if those changes that are not committed, that have been rolled out, have been seen by someone else? System failures, we not only had the applications, but we've lost all the memory state, and we guarantee that when you say update record blur, take $10 out of account 123, and I update a database record to do that, I do an update operation, I am guaranteeing that that is not being written back to the database. If I wrote that back to the database, performance would be terrible. So instead, there's layers and layers of buffering and caching. So I say, update that, and it says, sure, here's this page from the database, there's that record in it, oh, there you go, that page has now been updated. What I don't do is write it back to the database file on the persistent store, because I can't afford to do that. I could do it if I wanted to do 100 transactions a second. If I can't do 1,000 transactions a second and do that, it's just too slow. So I'm deliberately deferring writes, because I might get another update to the same page, in which case, hey, I'm only going to do one right now rather than two. Cool, I saved some I/O. So I do that for a while, and every now and again I say, I really need some memory. Oh, that page hasn't been used for a while, I'll write it back. Or I've got some clever mechanisms to try to make sure that when something does go wrong, I haven't got to go back through the last week's worth of transactions. So there are things called checkpoints and things so I'm trying to minimise the distance I've got to go back. So every now and again I'll write things back. But I guarantee that if I lose system memory, then the files that are meant to be keeping the persistent state will be out of date, because not everything's been flushed. And when I go to do a restart, of course, I only have the persistent state and not the stuff that was in memory. In memory is lost. Okay, how about implementing all this stuff? I don't implement consistency. The actual task of implementing all this is done by resource managers, RMs, and I'll use the phrase RM and TM around the place, and the coordination of resource managers, because I can have many of them on the one system, is done by transaction managers. So I might have a database, and it's a resource manager, but I also have a message queuing system which supports transactional message queuing operations. It's a resource manager. I might have another database system. I've got an Oracle one and I've got a MySQL one on the same machine, and they're both resource managers. And a transaction manager, its job is to tie them all together, to talk to all of them, to say, okay, you do this, that, here's a transaction context for you to tie this into, so that we can do atomicity and isolation across the lot of them. So that's the job of the TM. The two techniques we use are going to be locks and logs, and I'll talk about them in a moment. We use locks and logs combined to get atomicity. We use locks to get isolation, and we use logs for durability. They're the two things we worry about are locking and logging. The problem with locks is they're really intended for things which you get the lock, you do something quickly and release it. And which means if I'm running on a system, I need to trust that all the participants in that system will honour that promise. They won't grab a lock and then go out and make a cup of tea. Okay? So within a system, that's probably okay. Within an organisation, it might be okay unless there are physical problems about geography and latency and things, but I'm probably okay because I trust the bits of code in the system. But a distributed multi-party application, I don't think so. So we won't do that there. So locks are only really applicable when I have that. I can guarantee the participants will all honour the contracts about trust and timeliness. Our basic locking algorithm is that before we read something, we go and acquire a read lock, also called a shared lock. Before we want to update something, we go and get a write lock on it, also called an exclusive lock. And if we can't get one of the locks, we wait until we can get it. That's it. That's the locking. We want to read, before we read something, we get a read lock on it. Before we want to update something, we get a write lock on it, and we wait until we get the locks. That's it. Nothing more than that. We can only grant a lock request if it doesn't conflict. And read locks conflict with write locks. So I want to read something, but someone's already got a write lock on it, which means they're planning to update it. So I obviously can't read it because they haven't updated it yet. So read locks and write locks conflict. And write locks conflict with both read locks and write locks because someone else is already wanting to write it, therefore they own it. And I can't read it because it's in flight as well. So someone's got to go and look at what locks are there and whether this lock is allowed. And what they are physically are just bits of memory, bits of data, little data structure, and they are kept in lock tables inside the resource manager, and they're just bits of memory. And typically they will make use these days of specialised hardware primitives. Locking is so important that there are hardware support for them. So there are compare and set instructions, test and set instructions, other atomic instructions like atomic increment and decrement. Here's a counter, add one to it, and make sure one gets added to it. You know? Do whatever you need to do at a hardware level to make sure, even though you're reading, updating the value and writing it back again, that is atomic at a hardware level. So use those all the time. And you can combine things like test and set to do a spin lock, which is a common technique the resource manager will use. So I want to get a lock on something and say, for example, the lock table, which is itself locked by locks, I want to update the lock table. And I know that the code that's updating it only takes microseconds to do it. So I'll say, go and grab the lock. Oh dear, it's busy. Go and grab the lock. Oh dear, it's busy. And I'll just spin around testing and doing a test and set on the lock saying, is it free yet? Meanwhile, someone else on another processor is doing their thing and they say, yep, it's finished in 5 microseconds later. So I'm going to actually sit in a tight loop at a hardware level, just going, test it, test it, test it, test it, and jump back if it's not available. Why would I do that? Obviously, it's an infinite loop, right? Why would I do that? And the answer is, the alternative is saying, is it available? No, it's not. Go and ask the operating system to suspend me, put me on a queue, get me go through the scheduler, all of which might take several milliseconds to happen, when I know the lock will be available within a couple of microseconds. So I'd rather burn a bit of energy on a very short duration lock than go to the expense and time of being more polite about it. So spin locks are often used at that very lowest level in the lock implementation because they're dirty but really fast. So, and that reference there, I was looking around for a nice discussion of this, and that's a nice operating system level discussion about lock primitives and how they're used. And so there's a long history of it in computer science research of the dining philosopher's problem, and the words deadlocks come out of all that type of 1960s research. Locks impact directly on performance. There's a lovely phrase, I don't know whether I created it, but I use it. All computers wait at the same speed. It doesn't matter how fast your computer is, if it's got to wait for 10 milliseconds, it takes 10 milliseconds. It doesn't matter whether you have a 1 gigahertz machine or a 100 megahertz machine. If it's waiting for 10 milliseconds, it doesn't matter. So all computers wait at the same speed. So if I've got to wait for something, then I'm waiting. And that particular thread is stopped while it's waiting. And the worst case, I can get single threading, that these things are so conflicted that it doesn't matter how many processor cores I have available or how many threads, I'm doing one operation, then the next one, then the next one, because I've got to get a lock on this resource before I can continue, and everyone wants that lock. So I get the lock, I do 10 milliseconds worth of processing, release the lock. Well, the other 1,000 pieces of code that want to use that are doing the same thing. So I've got a queue 1,000 deep, all waiting just to get that single lock and wait and do their 10 milliseconds. And we'll talk about queuing theory next week. So I can get really bad behaviour and poor performance, regardless of the amount of computing resource I throw at it, as a result of using locks. And so I can get serialization of potentially concurrent transactions. And that's largely an application design problem, because you shouldn't have that much hitting on the same resource. These technologies are designed so that doesn't. Systems are intended not to have that type of problem. And a related problem is conflict redo loops, where I'm doing something, I've got my lock, that's all cool, I do stuff, and then something goes wrong because of concurrency perhaps. I say, oh, I'll try again. So I go back and try it again. So I can get a situation where I've got lots of these things all not waiting for each other, but they get partway through and interfere with each other. And then when they interfere with it, one gets interfered with, it gives up and goes back to the beginning of the queue again. So the end result is I get no forward progress. Every now and again one gets all the way to the end, but most of them don't. They get concurrency causes interference, and interference they stop and go back to the beginning again. So they can fail to thrive. They can not make any progress. So even if I say, oh, it doesn't matter, if I get a conflict, I will just give up and start again, that's good unless I get this problem. And the way out of all these problems is application design. And of course, locks gives me new application problems as well, new types of exceptions. I can get deadlocks. I have problems of resource starvation and waiting for locks. And there's a general question coming back to, who do you trust to take a lock on your system? It'd be a great denial of service vector on the internet for you to expose an API that someone can call, which will grab a lock on your system. Hey, I call that, hey, they froze, because I'm never going to release it. So you've got to be really trust and trust the code as well, that it will always be releasing locks. I'll talk a bit about that later. You'll notice when I do the examples at the very end that the transaction model there says, and here's a lock timeout, transaction timeout. I'm going to start a transaction. By the way, I'm giving it this long to run. At the end of that time, if it hasn't finished, it gets killed. And I'm doing that to stop that starvation, so that you can't start a transaction and then do a read line on the console saying, hello operator, what would you like me to do today, with a lock. If you do that, then the transaction will time out and you'll die. So, okay. Lock management. Resource managers. They keep lock tables. And so they keep track of all the locks in that they're responsible for. They keep track of locks that have been requested and locks that have been granted and what type of locks they are. And I mentioned the other day that we do deadlock detection, and the deadlock detection works by drawing a graph through this lock table. So you want lock this one, that lock is owned by that one. What else does that process own? Oh, it owns that one and that one and that one. And then, oh dear, we came back to a lock that you own, the new one. So we just trace a path through the graph of all potential locks, and that's what the resource manager is doing with that particular table. There's an example of that in the previous lecture. When we start going to distributed systems, then we can have distributed lock managers. And so now we have the lock manager sending messages to each other saying, someone wants to lock this, how are you going with that? So we've partition distributed the lock. And people like Oracle will do that. So if you have pair Oracle databases, they can have a distributed lock manager between them. It's probably too complicated, but it's worthwhile. Okay, what are we locking with a lock? Well, we can do fine-grained locks or coarse-grained locks. When these types of databases were sort of starting up, say when Oracle was starting, etc., then people often did table-level locks. There you go, I might update this table. There you go, have a lock on it. And of course that works fine, except that you don't get much concurrency. So people then move down. So each table is physically made up of pages. We'll do locks on pages, because that was considered enough overhead. But that gave you lock conflicts when people were trying to access entirely different records, different accounts, they were conflicting because of that. So let's go down to record level locking. So over about a decade or so, people went down the hierarchy, and now people mostly use record level locking. So that's great. So we get less contention and therefore better performance if we're doing record level locking. Unfortunately, now I have to have a lock in my lock table for every record that is locked in the system. So I might have hundreds of thousands of locks in the lock table, and traversing it is more expensive than managing it. So I'm paying in complication in the implementation of the lock manager by having lower level locking. That's why people did coarser level locking, but that was found to have performance problems. So there's a technique called lock escalation, where I start off doing the minimal level locking. I want to lock that record and that one. But as I keep on locking more and more, the lock manager says, you seem to have locked most of this page by now. I'll tell you what, I'll give you a lock on the entire page and release all the record locks. So it's just coalescing that group of locks and giving you one lock on it and releasing the lower level locks. So that's lock escalation, and most database systems will do that. So you do record level locking, but for efficiency, you'll escalate the locks up as necessary. Yeah, that's a worthwhile thing to do. And if you go and look at the documentation or some books on databases, they should spend a fair bit of time talking about these implementations. There's good documentation in SQL Server on this locking mechanism. I took those slides out, but they were in my previous version of this course. It's quite nice. If you're interested in technical computing, how you do complex systems, the implementation of locks and locking is quite nice. Isolation levels. In a pure world, this should not be a topic. There should only be one isolation level. One isolation level to rule them all. But instead, we don't. Isolation level, in the ACID isolation, isolation level says, how isolated do you really want to be? Because the more isolated you are, the more expensive it is to implement the isolation. There's a trade-off there. So there are, in the SQL standards, there are defined isolation levels, and you can turn the knob saying, I really want this stuff to be pure, so I don't have problems. Cool. Or I know what I'm doing here, and I'm willing to trade some possible problems that I have finessed my way around because I'm a smart programmer for better performance. So I can turn the knob back a bit. There are 4 such isolation levels. Uncommitted read, which says there is none. You can read anything. Someone updates something, hey, you can read it. Commit, doesn't matter. You can read any data, any state. No locks requested, no locks granted, really easy. You can read data that's about to be backed out by a failing transaction. If you read it again, it wouldn't be there because it's been backed out. You can see there's no consistency rules. Your view of that system has no consistency rules because you're seeing stuff that's in flight being updated. Why would you use this? And the answer is because you may not care. So what's the sum of all the balances in all the accounts in the bank? Well, I can give you a rough number. I can't give you an exact number without stopping the entire bank, which I'm not going to do. So if I'm only interested in a rough number anyway, I don't need to use locks on it. These sort of statistical numbers, it's fine. So, and it means I'm not interfering with any other transactions as well. So if I'm doing statistical approximate scans of large amounts of constantly changing data, that's a perfectly good isolation level to use, and it won't interfere with anyone else. But if you're trying to do sensible stuff and get to consistency, don't go there. Committed read, and that's a common default. It's what a lot of people have been trained to use. In committed read, when you say select something or read something from the database, you can only see data that has been committed at the end of a complete transaction. So you never get to see data that is being updated and might be undone. So we implement that by getting read locks before reading. So remember, read locks and write locks conflict. So if someone is updating something, they will have a write lock on it, and that write lock will not be released until the transaction has been committed. So read locks and write locks commit. So I'm trying to read data which is being updated. There'll be a lock conflict, and I will be forced to wait. So that stops me from reading data that is being updated and might be rolled back. So I can only see committed data, and in that world, I get a write lock before I update it and release it at the end of the transaction. The problem with doing that is that I do the same SQL statement twice, select blah, blah, blah. I can get different records each time. So there's no, because the next time I do that statement, more transactions will have finished and more of that data will be visible to me so perhaps I'll get a different set of results. And worse than that, I'm not keeping my read locks. So I say I want to update the value in account 123. So I say select the account record for account 123. Good, I've got that. That was a read, I've only got a read lock on it. And now I say, okay, get a write lock on 123 because I want to update it and do the update statement. In between me reading it and me getting the write lock, someone might have come in and updated. So, but I think it's $200. They've taken $100 out of it. I'm adding 50 in, and I add my 50 by saying, oh, it's 200. 200 plus 50 is 250. There you go. Update, store 250. And these locks won't stop that because I've released the read locks. I've got data, but normally I read something, add something to it, store again, and the thing I've read might be changing under me. So although that's a common default, I'm not very happy with it because it doesn't really solve my consistency problems. Repeatable read, next step up, is just like committed read, but if I read the same record multiple times, I'll always get the same value. No one can update it between me reading it once and me reading it again. That's why it's called repeatable read. And simply, I don't release the read locks. So I get the read locks, and once I've got a read lock, I've got a read lock. And I keep them until the transaction finishes. And when I want to update something, I get a write lock. And that might be a write lock over some data that I've got a read lock on, and I'm allowed to convert a read lock to a write lock because I've got a lock on it. I can try to anyway. I might get a lock upgrade conflict there, in which case I'll just have to wait, or I might get an abort, but at least I can try. So here I just go and get read locks, keep them, write locks, keep them. I can still get what are called phantoms, that if I do a query, select all accounts with balance over $200, I've got a set of records, I do that query again, it might be different because someone else could have added things in. So repeatable read is pretty good. It gives me good isolation, but depending on what type of SQL I'm doing, the sets of records I get back, if I want to do them again, might be different. And if I depend on the fact that that the sum of the things between account 100 and 200 were this, then that might change. But the last one of those is serializable. It's got a Z in it because it's American Standard. I'm sorry about the spelling error. And that's the full transactional isolation. And it's just like repeatable read, except now, if I do the same query multiple times, I will always get the same result as well. So I've effectively frozen the world I'm seeing. So no phantoms, that's good. And I do that by having a new type of lock, where I don't just have the locks on the actual data records, I also have locks over the indices which I use to order them. So I can say, I did a query over accounts 100 to 200 with serializable. I would get a lock over that range of accounts from 100 to 200, and that lock would stop other people from inserting into that space until I'd release the locks. So key range locks over indexes. Deadlocks. The resource manager, as I said, will do lock graph analysis when you're asking for a lock to see if there's a problem. And our solution, if we get a deadlock, is quite simple. We choose a victim and kill it. There you go. You look like a nice program. Whack. That's it. So it's sitting there waiting on some sort of operation which is asked for a lock to be granted to it. It gets an exception. it gets a deadlock exception back from that SQL statement or whatever it did. So it says, oh dear, I've had a failure. And what it's supposed to do then is say, I think I'll try again. And however it does that, it might just give up altogether. It might, and hope that something outside will retry it. It might have a loop where it says, here's my transaction code, here's the code, I'll just drop out of this piece of code and go back up there and try again. So it depends on how your system's built, but I'll retry. And that's great because deadlocks are normally transient, recoverable error, but there is a problem that with too much resource conflict that I'm wasting time and resources because that thing which gave up had done something. It had done computation and that's now wasted. So at least that lack of progress thing. So yes, the system has resolved the problem, but I've wasted time and I've been getting too many conflicts, then I get to the point where things are trying, dying, and I'm getting serialized execution, and I'm wasting a lot of energy and processor time on things which are failing constantly. Eventually they might get all the way through, but that'll be painful. Deadlock avoidance. It's obviously better to avoid deadlocks than to try to recover from them. It's an application coding problem. That's what we normally do in system software. It's an application problem. There's a fence. Let's throw it over the fence to the application programmer. And it turns out to be a hard one. It's good to define canonical locking orders, standard locking orders. For example, we can say we're going to be updating invoice stuff. So we have a rule which says if you're working on an invoice, you must lock the invoice header record. Once you've locked the invoice header record, you can update invoice detail items. But you've got to do it in that order. And if you do that, then no one's ever going to have a deadlock on that invoice area because two people want to work on the same invoice. One will get the header lock, the other one will not. And when the first one is finished with it, the second one can go and process the invoice. So by putting a rule in saying you must always get your locks in this order, you've avoided that particular source of deadlocks. It's a nice idea in theory, and definitely worth trying to do as a set of rules. But you think about a large, complex system, and think, oh, how do I? I've got I went to a Steelworks in New Zealand once. I was teaching a database course over there, and they took me into this room, and they had what you might call an ER diagram, a database diagram, and it covered all of one wall, all of the next wall, and all of the next wall. It was just this yay high. Oh, they were very proud of it. So I've got thousands and thousands of tables. How do I do that practically, and how do I decide what a good ordering is? So worth trying that, worth trying. And complex logic and complex systems make it very hard. And I can still get conversion deadlocks where I want to update, I want to convert a deadlock from one use, convert a lock from one use to another, and I can still get them. And right, I'm thinking about putting a build in there, but I didn't. So we normally, when we do selects, reads, we get read locks. And in that example I talked about where I said, I'm going to update account 123, so I select the 123, it's got $200 in it, I've got a read lock on that. And then I'm add 50 to it, and now I want to get a write lock because I need to do an update of that record. And it might be that I get a lock conflict when I try to do that. And I could also get the wrong value if they're to leave wrongly. So that conversion of the read lock to a write lock can fail. And I might get a deadlock on that. And there are things called locking hints. That's their word, that's their name, locking hints. And there's one of them there which is spelt that way, UPDLOCK, update lock. And so when you do the select, so here's my major problem. So I do a select, I go to the update, you can see that's a deadlock waiting to happen, and when I try to convert that, I'll fail. But if I put the word UPD lock in here, in that select statement, then I'll say, dear database, I want to do a select, I want to read that data, but when you do it, do an exclusive lock on it for me, because I'm going to later update it. So just giving it a hint saying, don't do what you normally do, which you just read. I want you to read it and I'm going to update it. So it just moves that lock forward. So locking hints can help there. Okay, how do we implement atomicity? We've talked about isolation. That's done with locks. How do we implement atomicity? How do we back out failing transactions? And we do that with a log. So what we do is when we update something, we remember what it was before we updated it. So here's my account record with 200 in it, and I'm going to update it to 250. I keep a record of the fact that it was 200. And then when I do the 250 update, I keep a record of this now 250. So those state changes I keep, and I keep them in a log. So I keep before images of everything which I've changed. And if I have to undo something, I simply go back and say, oh, that's changed, it's now 250, but I want to undo the 250. Let's go back through my sequential record of all the things that have changed. Oh, there's the previous value, it was 200. There we go. So I use a log of before state and go back through it to restore. It's not quite that straightforward, but that's basically what I do. So that introduces the very concept of a log. So what I've got is this thing called a log, which is just a file, and everything I change gets written to that log. Transaction. Sorry? There's transaction logs. Right? Transaction log, yeah. And so if I update something, I get before and after images of the thing I've updated. I'll do a commit, I'll get a commit record in there. If I delete something, it'll be, I've done a delete, and by the way, here's what it was before I deleted it. So all those changes in state to that data resource are recorded in that log. So on an application failure, I simply just go back and restore the before images to take me back to where I was. On system failure, I've got an inconsistent database. So I go to let's assume that there's things I'll worry about and I won't talk about just now, but I've got my database restored. I've now got to restore it to a consistent state because some of the things I have restored are updates from transactions that were in flight when the system failed. And I have to undo them because they're not consistent. So I simply have to take my log and say, oh, okay, that hasn't been committed, that hasn't been committed, that hasn't been committed, and undo them. So that's how I restore to a committed state. So the log logs everything that I've done, and I implement atomicity by using it by keeping records of commits when data is committed, and then by undoing back to committed points. So that's how that works. And it really only works if I have fully isolated transactions. There's this horrible thing, if I'm reading data which isn't right, it might be undone, then I've used that in another transaction, and then I get cascading problems. And we can get cascading aborts where, oh dear, that backed out, but I've used that, so I've got to undo this one, I've got that, and they're called cascading aborts, and they're not very nice. So, locking and alternatives. Maintaining locks is obviously complicated and expensive. And you really only need to do it if there is contention. And I said for performance reasons we want to minimise contention anyway, because contention costs you in things waiting on each other. So why do I have high contention data in my database anyway? It's a bad design. So what I might want to do is move it out of the database, or cache it, or use some other mechanism to avoid having really, really hot spots. Hot data is really bad for your performance. So perhaps it's an application database design issue. If you're getting high contention and poor performance, well, don't do it. It's like that guy goes to the doctor and says, "Doctor, it hurts when I do this." And, well, don't do it. It stops hurting then, right? So you're having problems with performance due to high contention and all the issues that come from that. Well, get rid of the contention. That's the problem. What happens if we don't lock? I mentioned this a couple of weeks ago. Can we just, if I've got a system where contention is a rare event, then I'm putting all this overhead into locking and etc., and it's a rare event. That's great. I have a really consistent, reliable system, but I'm putting a lot of overhead into handling something which happens rarely. So that leads us to optimistic concurrency control, where I say, things don't go wrong very often. I'll just fix them up when they go wrong. So optimistic concurrency control and variants thereof. So we don't use any locks at all, but we still have the idea of a commit or an update of some form, and we just do a check at commit time to see whether a problem has occurred, which means we need to have techniques for doing that. So we'll probably do something like, let's do an update sequence number on every record. So here's my account record, all the stuff you can normally see, account number, balance, etc. And in there is a number which is a version number of this record. So when I do the add $50 to it, it goes from version number 1000 to version number 1001. So now I've versioned every record in my system. And when I say I want to add $50 to it, I go grab account 123, its version number is 1000. I then go and update it, and I say, update this. By the way, I think you should be updating record 1000. And something says, oh dear, it's 1001. Oh dear, it's been updated. So then I can get an exception to that and try it again. So the idea is I have some magic thing, sequence number, a timestamp or something, on each record, and I check it to make sure that it's the right value. And that's a widely used technique. It particularly became popular with OONUS. So the Microsoft's Active Data Objects, ADO, it's an entity layer where I can cache bits. I go and do an object view of a world, and it sucks back things for me, and then I go and fiddle with the things that are in memory, and then at some point I flush them back out again. That model is using optimistic concurrency control. I keep version numbers, and the bit of code which is doing the write this back to the database is saying, okay, I think this record should be this version number, and it'll do some type of transaction-y stuff around that to be able to write them all back and check all the version numbers and say, whoops, everything is great or failed. In the Java world, it was a popular technique for entity beans, where I've got this entity layer and it is caching parts of my database for me for performance reasons. And because it's a cache, and there might be multiple people with their own caches and things the cache can get out of sync with the real database, and there's no overall locking and concurrency control there, that's fine. I just use versioning on them all and check the versions when I'm writing them back. And in a funny type of way is also what Oracle do. Most people who've done database level transactional support, the stuff we talked about, serializable, etc., have done it the way I talked about, using locks. Well, Oracle still use locks, but they've done something quite different, which in some ways is a version of optimistic concurrency control. But it's a very sophisticated version of it. So, and several people have done it. Alan has done some research work on Snapshot. Snapshot's quite nice idea. So what you effectively do is say, begin transaction. This is the theoretical way of what it does, right? It doesn't do anything like this. So theoretically, you say, begin transaction. It says, okay, I've frozen the database for you. Here is your frozen database. You do stuff on your database. The database you see is the database it was at the moment you did that begin transaction. And then you do stuff, and then you write it back, and everyone's cool. You effectively see a frozen snapshot of the database. That's why it's called snapshot isolation. And we do that with no read locks. So rather than grabbing read locks whenever we want to read something, no read locks at all. Still use write locks. But what we do is keep records of versions of things. So when you do the begin transaction, we get some magic thing which says, this is the time point that you see things at. Your BTR is now. And we keep, it's not really a timestamp, but it's effectively what it is. So this is the moment in time that we want to show you. And then in our data pages, we keep previous values. So account 123 had a balance of 200 and it was version number 1000 when you did the BTR. You may not have read it yet, but that's what it was. And you go away and do some stuff, and you want to go look at account 123, you see version 1000. It may now be version 1010, but you see version 1000. You see a consistent worldview. And it does it by saying, your transactional context is 1000. You want to look at that record. Oh, it's higher than that. Let me go back and look through the history of that page and find the one that corresponds to your worldview. So you're seeing it goes back in time for you to give you that consistent view. So the data pages themselves contain some previous data values. And you see the database as it was when you started your transaction. And if it's been changed, then you get the older value. But of course, you can still get up, when you say, I want to update things, then, and you're basing it on old data, you want to have something which is now changed, then you can get an exception on that. So you avoided one class of exceptions, but picked up another class of exceptions. But it's a clever idea.
If you're updating, you still have to get the latest version out of the database, right?
So
you can view the specific time stamps, your consistent view.
Yeah.
But if you want to update that, because there are updates, you have to get the latest version, right?
Well, you try updating it, and the update fails because you've based it on data that's been updated. So you're getting an inconsistent view of the universe exception back.
Right.
So I suppose they did it because at the time, this is when people were still thinking about, record locks would be great, but they're too expensive. So they thought, we'll get all the advantages of record locks without having to have all those read locks hanging around. So it was a clever idea at the time. And they still do it. And I would have to check. I vaguely think that SQL Server might have implemented as an isolation level as well. But several people have. It's an interesting idea. And it almost gives you full serializability. Almost. come back to that. So there's these transaction stamps. So we do a begin transaction, and we get a transaction stamp for me. You know, so you can imagine every time I update the state in the system, I increment a counter. So this is every time I do, say, a commit, I increment a counter. And that's what I get there. So what version of the committed state do I see? So I capture that, and then I can work out whether the record is before or after that. And then when I do a select, then I go and grab that record, say, is the timestamp in that record newer than the one I'm looking for, then go and back and search for an older one. And when I do an update, I try to get an update lock on the appropriate record, and if it is currently, if it's already been updated, then I return this exception. So it's a wash in performance today between conventional record locking and this. Oracle did it because it gave them good performance on less hardware back 20 years ago. And rather than waiting for a lock, when we want to do a lock conversion, we die. So you win some, you lose some, right? And, I thought I had a slide on that, but I took it out because it was far too complicated and technical. I said that it was almost full serializable. And the person who has written the papers showing how it is almost serializable but not quite is Alan Feckety. So one of his bits of research work was showing that defining the cases where snapshot isolation is almost equivalent to full serializable. And it's a thing called right skew. I did have some slides on it, but they're just too technical for this particular lecture. But ask Alan about it. He'll give you the paper. It's a pretty small area where it doesn't quite work. So, as I said, having hotspots, data hotspots, is a really bad idea always. And why have you got them in your system? What bit of data do you have that you're updating so frequently that everyone's waiting on it? And typically it's things like next record counters. So in the examples you've been using in the tute, we do the typical thing of having a record ID in every record. So username, a user number, item number. Everything has a number. Great. How do we get them? And one way would be to have a table of magic next numbers. We have a table, and row 1 of the table is next user number to use. Row 2 is the next stock item number to use, and etc. Great, a nice little table with all the next numbers in it, and it's part of the database, so I can update it under transactional control, and magic recovery stuff's happened. Everyone's cool. And every single update transaction is hitting it. And your performance will be abysmal because it's just a hotspot. I've seen systems where people are complaining about performance, and that's the problem, that they've got a magic record somewhere that a major path is going through, and they're serializing what should be a concurrent workload on updating that. That thing there is in every transactional path. So that's such an important workload that the database people said, we'll fix that for you. So depending on the flavour of your database, there'll be a magic word, like in SQL Server, it's identity. So you say, here is a key value, it's a integer, and identity. And you never set identity, it's set for you. The first time you insert something there, it gets the value 1. Second thing you insert gets the value 2. You never touch it. And of course, what it's not doing is keeping a bit of database state that is pounding on. It's keeping an integer in memory somewhere that it just updates. And it's doing it, it's kind, it's cool. It might lock it, it might not, depending on how the code's written. But it would take nanoseconds to update it. And it just gives you the next value with that transparently. The problem with that, of course, is that we've got to initialize it properly. Because system falls over. Ugh. Okay, what's the next account number? Oh, no. And what it's taking care of then is it knows that those account numbers are being monotonically increasing. So it's just got to find the last one allocated. After it's done all the commit cleanup stuff, it says, oh, what was the highest account number? 125. Cool. Next one's going to be 126. So it's doing a scan of the tables because it knows how those numbers are being allocated, and it will find the highest one allocated and then continue on from there. So its recovery is very easy. So that particular identity, and it's got similar names in Oracle, uses a different name. It might have a standard name in SQL standards. It's there just to avoid that hotspot because it was such a common problem. And summary information. Now, how many something or others do we have on hand, or even stock numbers? How many books are there? How many copies of this book are there? So every time I sell one, I've got to go to a stock level and update it. And perhaps if I've got really common items that are being updated all the time, that's a hotspot. How would I fix that? Perhaps have a light piece of library code somewhere that on initialization I set it and I update it, and then during recovery initialization I go and say, let's just count them again. It won't take long. It'll take 10 seconds to count them all, so I don't need to have a piece of data that I'm pummeling on constantly. But application program problem. So I might cache high contention data outside the database. And even if I've got to go and use locks and things on that, it's still better for performance. And the other trick is path length. I mentioned path length with Sabre. The number of instructions. So I've got a begin transaction and end transaction. There should be as little work done as possible between those 2 points, because I will have locks held while I'm between those 2 points. So the best thing to do is as little as possible. The shorter that path is, the better. So do I need to do file I/O? Perhaps. Do I need to do it inside the transaction? Possibly not. So I do push as much outside the transaction boundary as possible to reduce the path length of the transaction. Obtain my locks as late as possible. So structurally my code says, go and grab all the information I need to do this thing, begin transaction, do stuff, end transaction. Minimum stuff inside the PTR, ETRs. And, it's not very visible graph. Can you see the yellow line there? So a long time ago, with Ian Gorton, we did a whole lot of performance studies on transactional stuff. And this is a little graph from a real system. This would have been probably a SQL Server. And the 2 lines there, this one, I'm just allocating new records, storing new records away. The bottom line is the transactions per second I get when I'm getting the next number to use out of the database, and the top line is when I'm using the magic identity keyword. You see I've about there to there to there, it's a better point. So there, about a third better performance, 50% improvement in performance by going from hitting a piece of data really heavily to using identity. Okay, we're getting close to distributed transactions, the last bit of the stuff before that. Durability, the D in ACID, all based on logging. I talked about the log. That log not only lets me do atomicity, is also what I use to recover from failure. And we log everything, and all critical information fundamentally lives on persistent storage. We may well have copies of it in memory, and when we recover, we're going to recover from that log. I've got that. Next slide. Yep. One way of thinking of this is that when I've got a database, I actually have two physical copies of it. I have one physical copy which is easily damaged but is high performance, and one physical copy which is very robust and is abysmal performance. They're the two copies. One of them is the database tables that you would think of as the database, the files that had contained the pages containing the database, plus all the in-memory stuff, all the copies of those pages that are in memory that may be updated, may not be, etc., all the index blocks, etc. So that is a database. And altogether, it's a consistent, complete database. And that is there for performance. And one part of it is volatile. The other complete database is the log. The log, if you started off at the beginning of time, everything that's changed in that database, everything that's been added is all there in that log. That log is effectively infinitely long, but it's a log. It's impossible to use because you've got to go backwards and forwards through the log to find anything, but it's complete. And it's robust. We can have multiple copies of it. You normally write out multiple copies in parallel. You can ship logs off out of that system to a backup machine somewhere else. We can take a lot of care to make sure that log is robust. And that's really our durable database. So when we talk about durability, it's because we have the log. And we log everything, before images, after images, etc. And then when we come back from recovery, when we want to do a recovery, we go, there's two stages. The first stage is we've got the physical database tables in their files, and they are missing everything that was updated in memory. So they're a mess. So we use the log to take all the database files and bring them up to date to the last commit, to the end of the log. We just replay everything from the log. Now my database files are complete. They're inconsistent because they contain information from transactions that should be backed out. So then we just go back through the log and do the type of atomicity recovery from the end of the log and clean out any incomplete stuff. And then we have a completely recovered, up-to-date database. All just done through the log. Okay. Distributed transactions, which I said this was going to be about. So we've talked about locking, we've talked about logging, and we're going to bring these together to get distributed transactions. So we want all that good transaction stuff across multiple systems, and we want to have multiple systems working together on a single ACID transaction. And there are lots of questions there about whether it's going to be viable. Big one is trust boundaries. There are assumptions about the behaviour of other pieces of code. If they're not good assumptions, you're in trouble. There's latency assumptions, and there's questions of failure to be addressed. Because as soon as we have multiple systems, then they can fail in interesting new ways. They can fail to respond. Half my system might be working, half it might be down. We've now got a single transaction, and we're going to push it across multiple systems. So we're doing updates on databases on two different machines. But we want it to be ACID. We want it to meet all those nice criteria. So we've got to make it so that this distributed transaction still is atomic. They're still going to completely update. So the updates are going to be happening on both machines or on neither machine. It's still going to be atomic. And independent systems can fail independently. So we've got to cope with that problem. And the way we do that is we have, in our transaction manager, we implement a protocol called two-phase commit, 2PC. And 2PC is the protocol that the transaction manager uses to coordinate these sub-transactions happening on other parts of our system and to make sure we meet those requirements. So without distributed transactions, we're going to write an application that's going to move $100 from one account to another account. and it sends a message across to the Sydney system saying, take $100 out of that account, and that's a bit of application code, transactional. So it says, withdraw the $100, commit. The Sydney system is now locked in that $100 is gone. It's a committed transaction. Then we tell Melbourne, send Melbourne a message saying, deposit $100 in the account in Melbourne. Code starts doing that, and then something happens. It fails. And so that Melbourne transaction has failed. The Sydney one has committed. $100 has just gone missing. So that's why we need distributed transactions. Two-phase commit is called two-phase commit for the very good reason that it's in two phases. Phase one, we've got a number of participants, which are other transaction managers, by the way. So we have a TM talking to other TMs. Participants are all TMs. Phase one, the initiating TM asks the other TM saying, you know, you've got that commit there. Does it look good? Can you commit? And then in phase two, it says, okay, guys, commit. There you go, two phase. Ask to commit, go ahead and commit. And the transaction managers always know and record durably the state of that distributed transaction and their decisions. So once a TM said, yes, I can commit, it has recorded the fact that it has said it's going to commit. And if it fails and comes back up again, it says, oh, that's right, I was going to commit that. So when we say we agree to do something, all those stages are all logged in persistent storage so that when we have a failure, we can recover. So the TM asks all the other TMs, RMs to prepare to commit. The RMs, so it might go TM to TM to RM. The RMs involved will save their changes. They'll do a sort of preliminary commit and then say yes. And when they say yes, that's a promise. It's a non-breakable promise. Non-breakable because they've logged it. Any of those RMs, TMs can say no, in which case the whole transaction is aborted. But if they all said yes, then we go to phase two. Now, at the end of phase one, no one's actually done a commit. They've all just prepared to commit and written enough information in the durable log that they can commit. They don't know they've got to commit yet. They're prepared to. They've promised they can do it, and they're all prepared. So if everyone says yes, they get the order to go ahead, go to phase two. If any of them said no, then everyone gets told to abandon. Phase two, we just go ahead, and there's a nice diagram of it. Application program, it does a commit, goes to the TM sends out prepare messages to everyone. They all come back and say yes, then sends out commit messages. And all of that stuff is heavily logged. A successful transaction looks like the left-hand side. We do prepare, everyone comes back and says cool, and we do commit, and we do done. And a failing distributed transaction looks like the right-hand side, prepare, at least one of them says no, I can't for some reason, and then we send everyone an abort and we're done. And, whoops, wrong button. And there's a complicated state diagram which I won't go into now. Right, let's go back to here. And of course, there's lots of complication here, hence the state diagram. And the complication is always, what if something fails at a very inconvenient time? What happens if someone fails between saying they're prepared to commit and then when the commit message comes, they've gone? But the commit message has been sent out to all the others, so they've all gone ahead and committed. So now we've got a transaction where this system has gone and committed because it's been told to, and that one had promised to do so but has gone away. And the TM is waiting for that done message back from all the participants. So the TM, the coordinator, knows that Sydney had promised but has gone away. And when it next hears from Sydney, he's going to tell Sydney, by the way, you need to commit that. You made a promise, go ahead. So there's multiple layers of things, using the durable log to recover state and then recovering, hence the state machine, recovering the state despite failure. So someone's gone through and worked out all the possible places where we could get a failure and how we'd have to recover from that failure. But when you say, I'm prepared to commit, you must, despite whatever happens, be prepared to commit. And at some stage you may get a commit message. So, highly robust. I've used the word TM. What are they physically? It could be part of databases. Most databases, a lot of databases have inbuilt transaction managers. So Oracle does particularly, because they came up from a world where the database was it, and it did transactions, or it does distributed transactions, so they did TM functions. They can be part of a thing called a transaction monitor. So kicks, etc., are transaction monitors, and their sole purpose in life is to coordinate transactions and monitor them. It can be a standalone, just a distributed transaction coordinator. So in the lab this week, perhaps you did it last week, you were asked to start Microsoft DTC. You need it to do the distributed transaction for this lab. And DTC is a transaction manager. That's all it does in life. It's not a resource manager, it's just a transaction manager. So you do that. And you might find them in your runtime. Perhaps your J2E runtime or your .NET runtime might have a lightweight transaction manager in it as well. A few things there I'll talk about at the end as well. You can have multiple transaction managers. You normally would have one per node looking after the local RMs, and that gives you transaction trees because those TMs can call on it. They can invoke transactions on other machines, which might invoke things on other ones, etc. Right? So you can have whole branching trees of these things. So that's a good picture of it. And what we do, I wanted to go back to here because of this word here. We create a thing called a transactional context. That's the context. So when the initiating TM says, hi guys, I've got a transaction for you, that is the transactional context. And that's the one that's passed around, and the resource managers get it. So when they're doing their locks or whatever, as part of that transaction, they know that transactional context. So it's created when the first BTR at the outermost level is done, and then it's just propagated through the system. So transactional context is propagated. Yeah.
Is it correct to say the resource manager sits inside the database and the transaction manager is probably outside?
No. So if you're in Oracle world, then the TM is inside the RM. The RM and TM are one. But there's no logical reason why that is so. It's just historical. In the Microsoft world, originally, and then they might have changed things, SQL Server did not do TM functions. That was done by MSDTC. So they followed that model. Separate distributed transaction manager. But it's just a matter of how you're packaging it. Okay. Resources. These days we're mostly talking about databases, but of course it shouldn't have to be. Anything which you really want to evolve in that state should be covered somehow, and it's an application problem to work it out. So if I've got an ATM and here's my transaction, I do begin, someone says I want to take some money out, I do begin and do update the account, I somehow either send out a message somehow over some network to the ATM saying, go and issue $200 to the customer who's there. Great. And then before I get to do the commit, something bad happens. Well, the customer has the $200 in their hand, and you've just rolled back the update account transaction. So the customer's very happy. So I shouldn't do the dispense cache inside the transaction. That's silly. I'll move it outside. Great. Begin, update account, commit, crash. Oh dear, the customer just lost $200 because we haven't done the dispense cache yet. And didn't know where we put it. And let's go to, if we go back into ancient history, things like Kix and that, really old TP systems knew that problem, and they supported things like printing to printers, sending messages out over networks, writing to files, etc. Could all be transactional resources. So, and that required a lot of operating system coordination. So you go right to the file, and the operating system say, I know you're writing to the file, but you're inside a transaction, so I will defer those rights until the commit. And then we just stopped doing that because it was too hard. But the problem hasn't gone away. So now it's an application problem. So you still got to solve it. So we might do something like, we don't send out the message to the ATM, we write a message to another part of the database of requests for ATMs, different table, and then we commit. So now the message is in that table, which is part of the database, so it's cool. And then we have a background process, which is looking at that table saying, oh, I need to send some money out through an ATM. Good. And I'll do that as a background process. So now I've got two transactions working on a transaction resource. So perhaps that's the way I do it. I've mentioned message queuing, and message queues are there for just this type of purpose. I want to communicate something with something outside, and I want to send you the message, and I want to make sure it gets there, so I can do a message send on a transactional queue, and it's deferred until I do the commit. So I say, send the message to you inside my transaction, and the message is sort of sitting there waiting to be sent, but is not allowed to be sent until I commit the entire transaction. So I include the message sending in as part of the transactional resources. So that's pretty useful. And there are people who do transactional file systems still, so I can bring the whole file system inside a transaction, which is good. But it needs to be thought about. This stuff's pretty simple. Transactional API models, you've seen some of these. You can do explicit, begin, commit, or you can wrap it up and say, I've got a method here, and this method is a transaction in its own right. And the stuff that you're doing in the lab tonight, that's the way it's done. Here's some methods, and they are transactional methods. And every time I call them, a transaction will be started when I enter the method and finished when I leave the method. So that's a cleaner programming model, but obviously less flexible. Yep, I'll come back to that. And that's pretty common in today's component models. A lot of things become declarative, including transactionals. Talked a bit about this beginning of last week when we talked about state and stateless. We've talked about these little transaction programs. The request comes in. What are they physically? And the implementations vary a lot. So, and the answers will alter your performance and integrity, etc., and management. So sometimes they're the equivalent of little programs. These days it might even be a little VM. So this request comes in, something gets spun up from nothing. It might be coming into a container, and we spin up a container to just process this. And we process the request, and then we shut it all down again. That's one of the oldest models. As I mentioned Kix before. That's what Kix did. A request comes in, Kix starts up an instance of the program to run that. And then it runs, and then it kills it again. And because starting up a whole program, initializing it might be a painful process, then there's whole mechanisms there for fast startup and caching pre-started up programs, so it becomes a memory copy, effectively nothing else. And if that sounds like an odd thing to do, the original Unix-based web stuff was all that. The HTTP bump, and that request would go in and it would start a process up to process your web request. And then it would do it and response would go back and the program would go away. It doesn't scale very well, but it's a common model. Or we might have an application program sitting there, multiple copies of it, with a queue. Request comes in, gets put on a queue, and there's a number of copies of a program sitting on there dragging requests off a queue. And that's a good model because we might be able to do clever transactional stuff on the queue there, so that if we fail, the message goes back on the queue and another application can pick it up. So that retry mechanism now becomes really straightforward. So we might have multiple application programs fed from a queue, and then for management purposes, we can control the numbers that we have. We can turn a knob up and down to have more or less concurrent copies. It's really cool. We might be doing that by having a process, a hosting process, like a lot of the code you've been using does, and there's just a library. A request comes into the hosting program and says, oh, I need to call the library method that will process this. Yeah, lots of options there. And the method, it all has effects on performance, etc. Request integrity. So we've got a message coming in. We've got a series of messages coming in. There's a queue of messages there waiting to be processed somehow. Someone's got them. They might be sitting in buffers in network subsystem, or there might be some application sucking things off and putting them on an in-memory queue. What happens on failure when we lose it? We could well lose them. That's not an uncommon model. Oh, well, hasn't been processed. Things that were in flight are lost. We could have something which says incoming requests are logged as well as being queued, and on system failure recovery, we go back to the log and recover them. Because it now means we've got an extra I/O on every single incoming request, and we're doing thousands of them a second, so now I've got potentially an I/O bottleneck there where I'm doing thousands of writes per second just to save my incoming requests. If I am using transactional queues, then life's really easy because I'll recover automatically. Taking things off a queue is transactional. If I fail, they go back on again. So really easy management and recovery if I've got transactional queues. And it brings us to the lovely word, the word of the week, idempotency. It's really nice if you can write your system so that you can have the same request coming in multiple times, having exactly the same effect. Not a cumulative effect, but the same effect. That might be a rejection the second time, saying, oh, I've already seen it, but you can do things multiple times. And if you're doing an internet-facing thing, someone says, do this, and you go to buy something and it says, whatever you do, don't hit refresh now, because you might get billed twice. Because they've got some state which says go and bill them, and they get the request coming in saying go and bill. And they, okay, I really need to wait for that to complete. Because what people will do when they're not getting a response, they go, oh, I'll send that again, do it again. And if you allow people to do things again, then you solve some of those problems, and that's idempotency. So you might do it by having some magic thing saying, a number saying, this is request number 481. Have I processed 481? I already have. That's okay. I'll ignore it. But you may have to think about that as a way of coping with repeated requests and what happens with requests that have been submitted but have not been yet processed. How do you recover those? And lots of application questions there. Oh, we can nest transactions. People rarely do it, but there's academic technology there for risk. And just-in-time transactions, which is what basically the .NET and EJB stuff do. You just say this piece of code is transactional, and you come in and you get a new transactional context. There's nested transactions that people don't normally do it. So we've got a piece of code which is withdraw, it's a transaction in its own right. Piece of code deposit, transaction in its own right. And we've got another piece of code which is transfer, which is a transaction. So the transfer transaction is calling on the withdraw transaction and the deposit transaction. So they're nested transactions. And if you were doing that in a declarative model rather than an explicit begin-end transaction model, then all of those functions would be named as requires transaction. And then what we're going to be doing will, the withdrawal, when it gets called from transfer, it'll be passed a transaction context. So those methods will all be, the code at the beginning of them will all say, I need a transaction context. If I don't have one, I'll get one. If I do have one, I'll use it. So it's not quite the same model as that, but it's effectively the same. So here, the transaction context is created by transfer and then passed on to withdraw and deposit. So they're all working in the same transaction. And the database resource manager knows that they're all part of the same transaction. And the locks are all shared because they're all part of the same transaction. Okay. Almost finished. It's good. Get you out of here in about 2 minutes. Transactions are great things. They make programming much simpler. They get better reliability and correctness, and you can largely ignore failures and concurrency issues apart from the impact on performance. That's a nice summary of things I've already talked about. The last few points there, we're doing lots of logging, and logging can be a major performance bottleneck. And in the days of spinning Rust storage, then that was a considerable problem. It would limit the throughput of your entire system. Solid state storage is your friend, and you should have that stuff on solid state no matter what. And good performance of any of these systems requires both careful design and particularly avoiding traps. You can get good performance or bad performance out of the same technology depending on how you design your application. A two-phase commit, then commit can potentially take a long time. You've got at least 4 cross-network messages from the time you first take your lock to the time you're finished, and other concurrent transactions might be blocked for that whole period. So you've really got to trust everyone to be prompt, and the transaction coordinator might say, you've taken too long, I'm going to kill you, and start again. There's a bloke I'll talk more about later on called Pat Helland. Pat Helland's a lovely bloke. And I was at a meeting when we were talking about some of these web services transaction standards, and we were saying, WSAT, that's the unavailability protocol. You just cannot do it. And he's only semi-right, but he's a good guy. But in terms of web services, then you don't want to expose locks across an open network. Okay, that's probably a good spot to stop for tonight. Next time I'll do other transaction models, and then we'll do some performance stuff. Cool.